We'll be dealing with variable mass. Variable mass basically is a consequence of Newton's second law. D by dt of momentum will be written as m into v. So this becomes m into dv by dt plus v into dm by dt. So basically, till now we have been dealing with particles where mass is constant. Suppose if the mass is constant, you are dealing with only mass into acceleration. What if the mass is changing? This is what contributes to what we call as thrust force with the proper sign. So what is it that you would suggest as far as problem solving techniques are concerned? We would suggest, along with all the external forces acting on it, add one more force called thrust force and equate it to mass into acceleration. Along with all the existing external forces, add one more force called the thrust force. This thrust force will have a plus or minus. We will in depth analyze whether we'll have to add the thrust force or subtract the thrust force. Two important clarifications here is the thrust force will be Vr dm by dt. Vr is relative velocity relative to the original mass and dm by dt is the rate of change of the mass. Now suppose you consider a body. This is moving with a velocity of u. This body ejects a mass of delta m with a velocity Vr. Ejects, rocket propulsion. We are laying the foundation for rocket propulsion. So suppose the body somewhere in space is moving with a velocity of u. It ejects a mass of relative velocity Vr. When you know you have to conserve momentum with respect to ground, why are you taking relative velocity? Problem is, when the rocket is somewhere in space, ejection speed of the efflux you will get from the sensors placed behind the rocket. So the speed of the efflux will be got from the rocket's sensors. So what you measure is technically Vr. As a result of which, this will be m minus delta m. Simultaneously, the velocity of this changed to u plus delta u. U became u plus delta u. And you will conserve momentum. You will conserve momentum after finding the velocities with respect to ground. Right? This will be mu. Delta m into velocity of this with respect to this is Vr. With respect to ground will be Vr plus u plus delta u plus m minus delta m into u plus delta u. You have translated this velocity with respect to ground. Relative velocity with respect to this mass plus velocity of this mass with respect to ground. You will get this velocity with respect to ground. Inertial frame. Why with respect to ground? Newton's second law is applicable only for inertial frame. Delta m into Vr plus delta m into u plus delta m into delta u plus m into u, m into delta u minus delta m into u minus delta m into delta u. This is m into u. Basically, you will cancel out these both. Delta m into delta u, delta m into u. I am left with Vr dm by dt is equal to m into delta u by delta t. This is the force acting because of the variable mass. So we call this the thrust force Vr dm by dt. Now here you have to understand one very important point. You have categorically solved the problem for one specific case of decreasing mass. Mass can be increasing. Mass can as well be increasing. Can you give us an example of increasing mass? Conveyor belt, when mass is falling on the conveyor belt. So mass can be increasing, mass can be decreasing. So in general, having taken one particular condition here, the negative sign which I forgot, have a look at it. This plus this is 0. Obviously, I will have a negative sign. The negative sign tells me that if the mass is decreasing, if mass is decreasing, thrust force is opposite to the direction of relative velocity. If the mass is decreasing, you took the example of decreasing mass, thrust force is opposite to the direction of relative velocity. How do you want me to remember this? Quite obviously, you will remember if you remember rocket propulsion. Mass of the rocket is decreasing. Thrust force will be opposite to the direction of relative velocity. On the contrary, if mass is increasing, thrust force is in the direction of relative velocity. If mass is increasing, thrust force is in the direction of relative velocity. We will take both the examples to explain this. First of all, this is the standard derivation. Take it down till here. So, in general, whenever you are involving a problem where the mass is changing, mass is varying, that too continuously, you will add along with all the existing forces one more force called thrust force. Procedure to be followed is, along with all the existing forces, you will add one more force called the thrust force and equate it to mass into acceleration. So F external plus or minus the thrust force is mass into acceleration. Plus or minus, how do you decide? I will again reiterate the sign convention here. If mass of the system is increasing, thrust force is in the direction of VR. If mass of the system is decreasing, thrust force is opposite to the direction of VR. Let us take an example like this. This is a trolley. There is sand spilling into this car. Sand spilling into this car from a fixed funnel Initial mass of the cart is taken as m naught. Mass is falling at the rate of mu kg per second. You are pulling this with a force of F. Everything starts at time t equal to 0. At t equal to 0, you applied a force. At t equal to 0, sand starts falling into the cart. At t equal to 0, the cart starts moving. Initial velocity u is 0. At t equal to 0, initial velocity of the cart is 0. You start pulling the cart, start applying the force also at time t equal to 0. We are interested to calculate velocity of the cart as a function of time. Velocity of cart as a function of time. Let us write the dynamic equation first. What did I tell you? Along with all the existing forces, add one more force called the thrust force. Equate it to mass into acceleration. So, after time t, in a short time interval dt, let the velocity of the cart be v. At this instant, I should know the relative velocity of the sand particle with respect to the cart. Velocity of the sand particle with respect to the cart is velocity of the sand particle minus velocity of the cart along this direction. Velocity of the sand particle in the horizontal direction is 0 minus velocity of the cart is v. So minus v. Try to understand the significance of this negative sign. The sand particle with respect to the cart will have a velocity of v in the backward direction after time t in a short time interval dt when the velocity of the cart is v. Sand, for instance, a person standing here will feel that the sand particle is moving in the backward direction with a velocity v. And what was our sign convention? If mass is increasing, thrust force is in the direction of relative velocity. Relative velocity of the sand particle with respect to the cart is in the backward direction. So thrust force is in the direction of relative velocity. So technically your cart will have a free body diagram like this. You are pulling with a force of F and thrust force is in this particular direction. Because the sand particle's relative velocity will be v in the backward direction. If the mass is increasing, thrust force is in the direction of relative velocity. Your dynamic equation will be F minus the thrust force is mass into acceleration. F minus thrust force is Vr dm by dt. M naught plus mu t into dv by dt. Concentrate on this. I will not again put a negative sign here. This already involves the direction. Vr dm by dt, I have taken the magnitude. Negative sign because of the direction of the thrust force. Dm by dt is the rate at which sand is spilling into it. F minus mu v. And what is the value of relative velocity? It's equal to v. Velocity of the cart will be equal to m naught plus mu t into dv by dt. After time t, in a short time interval dt, this will be the mass. M naught was the initial mass. Mu is the rate at which mass is falling onto the cart. So presently after time t in a short time interval dt, this will be the mass. dv divided by f minus mu v is dt upon m naught plus mu t. At time t equal to 0, velocity of the cart was 0. At time t equal to t, find the velocity of the cart was the question asked. Ln f minus mu v upon minus mu. I'm damn sure you people know the integration of integral dx upon a minus bx. This is 0 v is equal to ln of m naught plus mu t upon mu. This will be 0 to t. These both will get cancelled. Take the negative sign here. It will become f minus mu v upon substituting the limits of v and 0. F minus mu v upon f is equal to m naught by m naught plus mu t. Why did you take the reciprocal of this? You have taken the reciprocal because of the negative sign. This negative sign coming here will go to the power ln of that particular power. Cross multiply and find out velocity as a function of time. Take it down till here. Simplify even this part after cross multiplying and write the expression for velocity. You obviously can make a guess as to what the next question would be. The next question would be a system where sand is spilling out of the cart, mass is decreasing, sand spilling out of the cart. Take it down till here, I'll explain. What if sand is spilling out of the cart? There is a very popular mistake committed by the students there. When the sand starts spilling out of the cart, I start applying a force at time t equal to 0. Sand starts spilling out of the cart at time t equal to 0. Velocity at time t equal to 0, u is 0. Everything starts at time t equal to 0. Spilling of the sand, the force applied, initial velocity 0. Everything starts at time t equal to 0. Popular mistake committed by the students here is, if mass is decreasing, thrust force is opposite to direction of relative velocity. So here when you take after time t in a short time interval dt, let the velocity of the cart be v. Here students by mistake consider the thrust force to be in the direction of the force or sometimes opposite to the direction in the backward direction. Both of them are a mistake because relative velocity is in the downward direction. VR is in downward direction. We are in horizontal direction is 0. That's the most important point. We are in horizontal direction is 0. When the sand particle is spilling out of the cart, velocity of the sand particle, velocity of the cart, both of them will be the same. So relative velocity of the sand particle with respect to the cart will be 0. So thrust force in the horizontal direction will be 0. Rocket propulsion, you send, it is not sand spilling out. In rocket propulsion, you pressurize the gas to push it down so the rocket will go up. Here sand, if it is pressurized to move downwards, then the cart will fly in the upward direction. If sand is just spilling, the velocity is not surplus for the cart to fly in upward direction unless and until your Rajnikant. Here VR is in the horizontal direction, which is 0. So there is no thrust force at the first place in the horizontal direction. Then why are you covering it in variable mass? You shouldn't have covered this in variable mass. Problem is mass is decreasing. Mass is decreasing, but there is no thrust force. Whenever mass is decreasing, don't always assume that there must be a thrust force in a particular direction. For instance, best example is this. So here, thrust force is 0. F is equal to m naught minus mu t into acceleration dv by dt. dv by f is dt by m naught minus mu t. At time t equal to 0, the velocity is 0. Time t equal to t, I want the velocity as a function of time. V minus 0 divided by f is ln of m naught minus mu t upon minus mu, limits 0 to t. V by f is ln m naught minus mu t minus ln m naught upon minus mu. Remaining simplification, I leave it to your fine judgment. Finding out the velocity as a function of time. Now, interestingly, what I have found with the students is, now after finding out the velocity, if I ask for acceleration, all smart kids differentiate the velocity with respect to time and get the acceleration. You already have the acceleration. Don't do the simplification again. Bring this to the denominator, that's your acceleration. From acceleration, you integrated and you got velocity. Now you ask me for acceleration. You will differentiate velocity, go back till here and get back the same expression. Please don't do that. Just to bring this to the denominator, that will be the acceleration as a function of time. You don't need to differentiate this velocity again. In fact, you integrated that acceleration and got the velocity. Take it down till here. Now, majority of the problems in this subtopic come from chain related problems. Whole of the game starts here. They'll tell you a chain is released this way and the chain doesn't form a heap. Chain doesn't form a heap. Why do they tell you chain doesn't form a heap? Because shape of the heap is undefined. It can be arbitrary. The heap we assume is a conical shape. Need not be a conical shape. It may be a hemisphere. It may be a distorted figure, so on and so forth. So they'll tell you when the chain is falling, heap is not created. They want to know force exerted on the floor as a function of, if this is x, this will be x. They want the force exerted on the floor. I will solve this problem in two ways. One, using variable mass. Two, using the fundamental concept of change in momentum. First of all, suppose if a student is comfortable using variable mass. By the way, what is the question? Force exerted on the platform. Force exerted on platform. At the first instance, students feel it is the weight of the chain on the platform which is the force exerted. Along with the weight, there is a small element which is striking the platform and coming to rest. I repeat this line, pay attention. Along with the weight of this part, lambda x into g, where lambda is the mass per unit length. Along with the weight of this part of the chain, there is a small element which is striking the platform and it is coming to rest. There is change in momentum for this small element. This small element change in momentum contributes to a force. So if I go from the fundamental concept, this will be dm into v minus 0 by dt. Very orthodoxly, this is the final momentum, this is the initial momentum. Why didn't you write final minus initial? It's only a negative sign. And I know the direction of the force exerted by this chain on the platform. So I am not worried about the negative or positive sign. Dm lambda dx v upon dt lambda v square. This is the way I go from the fundamental concept of change in momentum. Some students feel you can directly calculate the thrust force. What did you tell me thrust force as? VR dm by dt. Here the platform is at rest. This will be V dm by dx into dx by dt. dm by dx mass per unit length. Dx by dt will be v lambda v square. So either way you are getting the thrust force to be lambda v square. And what is the velocity? V square is equal to u square plus 2ax. Initial velocity is 0. 2gx v square. So thrust force will be lambda times 2gx. This is the thrust force. Thrust force is coming because of the change in momentum of this small element which is striking the platform. Other than that, there is a length of the chain on the platform. Net force will be 2 times lambda gx plus lambda gx. This will be 2 times weight on platform plus weight of chain on platform. Or you can directly write the net total force to be 3 times weight of chain on platform. 3 times the weight of the chain on platform. Either you tell me that the thrust force is 2 times the weight of the chain on the platform, or total force will be 3 times the weight of the chain on the platform. Second, thrust force, either you calculate from VR or you calculate from the fundamental concept of change in momentum. We are okay either way. Lambda v square is a popularly used expression which you will have to remember as far as the chains are concerned. Now, where does the question become tricky? What if the platform was moving? Here, relative velocity became the velocity of the chain because the platform was at rest. What if the platform is moving? Then I have to take the relative velocity. You obviously know the next example will be a situation where the platform is moving. Take it down till here. Now, when you look at this question, the platform is at rest. Second point, you found out the force as a function of x, length of the chain on the platform. X is the distance it fell, implies x is the distance or length of the chain on the platform. We'll try to make a small change in it. Same problem, platform starts moving upwards. It's like you're dropping a chain inside an elevator. It's like you're dropping a chain inside an elevator. And to make it look like a new problem, we'll ask you force exerted on the platform not as a function of x but as a function of time. In this problem, you found out force as a function of x. Now I am asking you force as a function of time. Suppose this is the chain. The moment you drop the chain, the platform starts accelerating upwards. The moment you drop the chain, the platform starts accelerating upwards. Simultaneously, chain is falling with an acceleration of g, platform is moving up with an acceleration of a. Force exerted on the platform as a function of time. Chain also falls by some distance. Platform also moves up by some distance. And what did they ask you? Force exerted on platform as a function of time. Here we are not asking you as a function of x. We are asking you as a function of time. Now, firstly, what is this length? Half gt square. You are now taking it as a function of time. What is this length? Half at square. So what is the length of the chain on the platform? Half gt square plus half at square. First part of the problem is weight of chain on platform. Weight of the chain on the platform is mass into G. Technically G effective. This is the second point where students repeatedly go wrong. Mass of this chain will be lambda into half gt square plus half at square. This is the mass. Students commit the mistake of multiplying this with the g to get the weight. That will be wrong. It will be G plus A. Remember, recollect, man standing in a lift in Newton's laws. When the elevator is going up, normal force is M into G plus A. Here, the platform is accelerating upwards. The weight will be mass into G effective, that is G plus A. This will be lambda by 2 g plus a whole square t square is the weight of the chain on the platform. This is not the total force exerted. There is one small element which collides with this platform and comes to rest. So you have got thrust force which you already derived as lambda v square, but technically it will be Vr square. Then in the previous problem, why did you take V? Because the platform was at rest. Lambda relative velocity of this element with respect to this is gt minus of minus 8. Velocity of the small element is gt. Velocity of the platform is 80. Velocity of the small element is gt. Velocity of the platform is 80. And both of them are in the opposite direction. So lambda g plus a whole square t square. This is the thrust force. Net force will be lambda by 2 g plus a whole square t square. Lambda g plus a whole square t square. This will be the net force acting on this particular platform. Here we calculated this as a function of time. Key catch, take away from this problem, relative velocity is the key catch. If the platform is at rest, the velocity will be velocity of the chain. If the platform is not at rest, velocity will become relative velocity. Take it down till here, I'll make it a bit simpler. Now in this set of problems, direction of the force exerted by the chain was never a doubt to anyone. A body is falling on the ground. Chain is falling on the ground. Chain exerts a force on the ground in the downward direction. The platform exerts a force on the chain in the upward direction. That's never a trouble. So here mass is increasing, mass is decreasing. You need not touch this concept. As far as chains are concerned, you will never have a doubt regarding what is the direction of the thrust force. If you go from the fundamental concept, you don't even need to see if the mass is increasing or decreasing. Can you take a simple example to explain that? Have a look at this. There is a heap of chain kept here and I am pulling this with a force of F in the upward direction. I am lifting the chain. If I am lifting the chain with uniform velocity, which will be V. You are asking me what is the force I should exert so that I am lifting the chain with uniform velocity. At the first instance, the students will feel it is only lambda x into g. The force I exert should be equal to the weight of this hanging part of the chain. Obviously, if I want the marker to move with uniform speed, the force I exert should be equal to the weight of the marker. But here there is something else adding up. I'll split the diagram for clarity. This is the hanging part of the chain. This is the heap of the chain. This is the hanging part of the chain. I am pulling this with a force of F. Now one small element of the chain which is at rest suddenly starts moving. I repeat, pay attention to this. One small element of the chain which is at rest suddenly starts moving with a velocity v. There is a change in momentum. If there is a change in momentum, there is a force. Now here, though it is variable mass, I will go from the fundamental concept to decide the direction of the thrust force, which will make my life much simpler. Watch out for this. Small element of the chain is being pulled in the upward direction. That element will pull the chain in the downward direction. I repeat, mass is increasing, mass is decreasing. Don't get into those things. A small element of the chain is being pulled in the upward direction. That element will pull the chain in downward direction. Every action has an equal and opposite reaction. Action and reaction will never be on the same body. Action is on the small element. Reaction is on the vertically hanging chain. So now you ask me this. This will be weight plus thrust force. Weight is lambda x into g plus lambda v square. That will be the force exerted for me to pull the chain with uniform velocity. This example is mainly taken to explain the direction of the thrust force. Life will become really simple if you take a small element and see the direction. Can you make the reverse of this problem look very difficult? The simplification will be quite tricky. The reverse of this problem, I will tell you first, make a note of it. The same example, they will give you a chain being pulled this way with a force of F. What is the force to be exerted for it to be moving with uniform velocity? People assume there is no horizontal force. There is. Here there is no weight. If this length is x, that matters not. But a small element of this chain, if I draw the free body diagram, small element of the chain which was at rest suddenly starts moving with a velocity v. There is a change in momentum. That change in momentum will be the thrust force. So on the small element, the thrust force is towards the right. The reaction of that will be on the chain towards the left. So force exerted will be equal to the thrust force. Lambda v square will be the force exerted on this part of the chain for it to be moving with uniform velocity. Here weight also will add up. Here there will be no weight component because I assume that the chain is on a smooth platform or smooth surface. Take it down till here. Two typical problems where I'll take you people for a ride. This is a table with a hole on the top, smooth hole. On the top of the hole, you'll have to listen to this question, you will be solving this. In the sense, I'll give you the equation, all you have to do is simplify the equation. How many equations do we have to simplify? One equation. You're sure you'll be able to do it. There is a heap of a chain kept on the top of the table. From underneath the hole, you slightly pull the chain and release it. There are quite a few intricate concepts in this. Pay attention to this. From underneath the hole, you slightly pull the chain and release it. The chain starts falling. Question asked is find velocity of chain as a function of x. Find velocity of the chain as a function of x. As the chain is slipping down, I need to calculate the velocity. First idea that strikes to you people is loss in potential energy is equal to gain in kinetic energy. You have done such similar problems in work energy theorem. Chain slipping off a table. Here you cannot conserve energy. Why do you say that? Because I don't want to conserve energy. No, it's not about my likes and dislikes. Here, the heap of the chain on the table and this chain, I am separating these both. A small element of this chain which is at rest suddenly starts moving in the downward direction. That's an impulsive force. It is more like an inelastic collision. A chewed bubble gum, when you throw it towards the wall, it sticks to the wall. It is an example of perfectly inelastic collision. Energy cannot be conserved. Same chewed bubble gum, if it flies out of the wall, it created energy. Such a thing doesn't happen. Energy is not conserved. So a small element of the chain suddenly started moving. It is an example of an inelastic collision. Energy cannot be conserved. Loss in potential energy is gain in kinetic energy doesn't apply in this case. Then work energy theorem, there was a chain slipping over a table which you conserved energy. Their whole of the chain was moving with the same speed. There is no situation of an inelastic collision there. There is a categorical difference between the two. This concept should be clear. Here, small element of the chain suddenly started moving. There is an impulsive force here. And it is an example of inelastic collision. Then now let's rebrush what all we have learnt till now. Conservation of momentum, you will tell me I cannot do that here because there is an impulsive force and there is gravity. Gravity is non-impulsive but you are giving surplus time. Once you are giving surplus time, gravity also can produce change in momentum. Work energy theorem, you just now eliminated the option. What else did we learn in mechanics? Dynamic equation. Now to write the dynamic equation, have a look at this. Weight of the chain lambda x into g, thrust force in the upward direction. Once again, mass is increasing, mass is decreasing. Don't go by that. Go from the fundamental concept. Small element of the chain is pulled in the downward direction. That element will pull this chain in. Every action has an equal and opposite reaction. It's a direct hit. Avoid the confusion here. My equation is lambda x into g minus thrust force is lambda x into dv by dt. Straight hit Newton's law statement. This is where you started today's lecture of variable mass, stating that along with all the existing forces, add one more force called thrust force, equate it to mass into acceleration. Thrust force here will be lambda v square, lambda x into dv by dt. Do you have any other equation in your mind? Whatever we have learnt till now, Newton's laws, dynamic equation, constraint relations don't apply here. Circular motion chapter doesn't apply here. Work energy theorem you eliminated, stating that this is an example of an inelastic collision. Conservation of momentum out of question. So there is nothing else in physics I know that you can apply. You have only this equation. From this equation, you have to find out v as a function of x. Find out velocity as a function of x. I'll help you out to some extent. You can cancel out lambda. If you need some more help, I will go one more step ahead. I will write dv by dt as dx by dv by dx into dx by dt. Chain rule. Why are you doing it? Because you want it as a function of x. So eliminate time. Dx by dt will be velocity x v dv by dx. Find velocity as a function of x. This is called simplification. Let's see if you can do it. I am waiting for you people. I'll give you 5 minutes. It's not an easy task. Put all your skills of simplification to test. Let's see if you can get velocity as a function of x. Come on, you can do it. It is just one equation. Now listen, multiply all throughout by 2x. 2x v square. 2x square v dv by dx. You multiplied all throughout by 2x. So this is 2x square g, 2x v square, 2x square v dv by dx. Can I write the right hand side as d by dx of x square v square? U into v differentiation. I kept v square as it is, differentiated x square with respect to x. It becomes 2x. Now kept x square as it is, differentiated v square with respect to x. 2v into dv by dx. U into v differentiation. Kept v square as it is, differentiated x square. This is 2x. Kept x square as it is, differentiated v square. 2v dv by dx. This is 2x square g. 2g x square dx d of x square v square. Integral dx is x. Integral dy is y. Integral d of x square v square is x square v square. Integration and differentiation will cancel out. Though that's not the right language. 2gx cube by 3 is equal to x square v square plus some constant c. V will be root over of 2gx by 3. Now here comes the $1,000,000 question. How will it strike to us that we have to multiply this with 2x? Once mathematics people teach you people differential equations in 12th standard at the end, this idea will by default strike to you people. It's an art of writing this as a perfect differential. Just as in integration, you people are taught standard substitutions. Substitute this, you will get the answer. How does it strike to us that we have to do this substitution by practice? You will get it. Same applies here. It is unfair that I ask you people to do the simplification at this stage. Once differential equation, linear differential equations are taught, you by default will be able to simplify this. Don't get disheartened. Velocity root over of 2gx by 3. This we are able to recognize as d by dx of x square into v square. This is d by dx of u into v. Product rule, d by dx of u into v, u into dv by dx plus v into du by dx. This when I open up, I will get this. So whole of the game is recognizing the reverse simplification. Listen to one very important parameter here. This example is picked up from a book by name 200 Puzzling Problems in Physics, Cambridge University Press, Grande. What they did to this problem is, they said this is a carpet kept on a horizontal platform. This carpet from here is picked up and it is bent. This carpet from here is picked up and it is bent. This is picked up and it is bent, and you are pulling this with a force of F. The carpet doesn't slip. The height can be negligible. You are not doing any work in picking up the carpet. It's more like telling you that this is what we are doing with the. Are you able to visualize this? This is what you are doing. The carpet is being pulled in this particular direction, right? They asked you, what is the force? If this distance is x, what is the force exerted for it to be moving with uniform velocity? What is the force exerted for it to be moving with uniform velocity? Mind you, the question is from a book by name 200 Puzzling Problems in Physics. So for sure the answer is not lambda v square. What are you saying, sir? You said a heap of chain and the chain is pulling with a force. You are pulling with a force of F. Here it was lambda v square. Now here you tell me it is not lambda v square. Something drastically changed from here till here. Try to find the difference between the two. I will give you few minutes to think over it. It's not easy, highly non-intuitive, but give it a try. You have few minutes to think about it. Don't keep folding your books, that won't give you an idea. Look at the diagram. Think mathematically, you will be convinced here. Visualization will be almost impossible. Learning is all about perception. I will show you this right now in this example. If I make one change, you will be able to visualize this way. One small change I make, you will visualize it in a second. If not, you can visualize it only mathematically. Think about every possible case. Answer is not lambda v square. Answer is not lambda v square. Please think carefully. If I tell you the answer directly, you will miss an opportunity of putting pressure on your head. Now listen. The catch in the problem is dx by dt is not v. The catch in the problem is dx by dt is not v. Have a look carefully. If I have folded this, can I claim this length to be x and this length to be x? I'll take this length to be y. Length of the carpet is 2x plus y. dl by dt plus 2 time equal to dx by dt plus dy by dt. dl by dt will be 0. Length of the carpet is constant. dy by dt, this end is fixed. Carpet is approaching this end with a speed v. Technically, dy by dt is v, not dx by dt. dx by dt minus v. Y is decreasing at the rate of v. dx by dt is not v. So technically dx by dt is v by 2. That's the main catch in the problem. Even 200 puzzling problems in physics did not describe it this way. They just gave a verbatim statement stating that this dx by dt will be v by 2. Unless you show this mathematically, you will not understand this. Now, listen carefully. Learning is perception. Same carpet and chain, if I keep it in the vertical direction, you will visualize it in a second. Visualizing in the horizontal direction is so very difficult. Observe this visualization. If I give you a chain like this and I tell you that chain on the right side is dropped. Now ask the student, This went down by how much distance? Spontaneously you will tell me x by 2. This x length, half goes this side, half goes this side. Same problem, make it vertical, you visualize it in a second. Perception is so very concrete in human mind. Here you put it horizontal, it becomes difficult to perceive. Have a look at it. If x length has fallen here, x by 2 goes this side, x by 2 goes this side. So this end moved by how much distance? X by 2. So if I tell you the velocity of the chain here is v, the velocity here will be v by 2. As simple as that. This is not difficult to perceive. While this becomes difficult to perceive, by the by, F will be equal to here the small element thrust force. What makes you say thrust force is in the backward direction? The small element at rest is being pulled in this direction. Thrust force will pull it in backward direction. Right? Small element is being pulled to the right. This element is being pulled to the left. Thrust force will be V R dm by dt. Now VR, here comes the difficulty. Dm by dt you will replace with lambda into x. Dm by dt, this length is x. Here we mistake dx by dt to be v. Here dx by dt is not v. Here dx by dt is, I proved here mathematically. Here I made you perceive this, making it vertical. Dx by dt is v by 2. So the force I need to exert for that carpet to move with uniform velocity is lambda v square by 2. Is this point clear? It's a well laid trap, difficult to perceive, but once understood mathematically, should not be difficult thereafter. Last but not the least, derivation of rocket propulsion. It in itself has a controversy with a negative sign. I will do the derivation, take it down till here. Can I rub the board? This is a rocket. Mass of the rocket is capital M, right? The thrust force will be Ft, quite obviously. The thrust force, where relative velocity is in the downward direction, mass is decreasing. So you would write your dynamic equation is Ft, sorry, yes, Ft minus mg is equal to mass into acceleration. Only one assumption I am making, g is constant, which need not be the case in the case of rocket propulsion. Right now, gravity chapter has not been taught to you gravitation, hence we are keeping g constant. Variation of g will be dealt with in the chapter gravitation. Thrust force in the upward direction, we are dm by dt minus mg is m into dv by dt. Thrust force you have already taken the direction. Thrust force you have already taken the direction. Right? We are dm by dt. It's here 99% of the books without giving proper clarity will put a negative sign and they say because the mass is decreasing. Now this is not fair at the first place. You already took the direction because the mass is decreasing. Now again you put a negative sign and tell me the mass is decreasing is not fair. Am I right? Yes or no? Problem is what they don't explain is this is small m and this is capital M. Small m plus capital M is the total mass of the rocket m naught constant. When I say dm by dt plus d capital M by dt will be 0. Now you are replacing dm is the small elemental efflux which is coming out, while d capital M is the mass of the rocket. So when they say mass is decreasing, what they meant is decreasing mass of the rocket. Here in the thrust force, what you have is dm by dt, d small m by dt. Now divide all throughout by m minus Vr dm by capital M minus gdt or gdt plus dv. I divided by m all throughout multiplied by dt. I should have bought it this side. It's okay. I'll write it again. No issue. What did I do? I divided by capital M. Divided by capital M. Multiplied by dt. I have dt here and this is gone. My requirement is velocity. So I keep this here. Minus gt is equal to dv. dv is equal to minus gt minus vr dm by capital M. At t equal to 0, velocity is not 0. The spacecraft already burnt out some mass of the fuel. Initial mass is m naught. At t equal to 0, velocity is u and m naught. This is m at time t. This will be V minus U minus GT minus of VR ln of M by M naught. V is equal to U minus GT plus VR ln M naught by M. A standard expression as far as the rocket propulsion is concerned. The only controversy is 90% of the books don't give you a clarity as to why d small m by dt became minus d capital M by dt. They write mass is decreasing. Write it this way. Now it will be 100% clear to you why you have introduced a negative sign. Second, all throughout in this equation, now capital M is the mass of the rocket, not the mass of the flux. But when you wrote the thrust force dm by dt, this dm is the mass of the flux which is coming out. Hence, the negative sign has significance. Now you get the correct equation as far as rocket propulsion is concerned. Rocket propulsion. Only assumption here which is slightly unreasonable is G is constant is an unreasonable assumption, but you are taking for a short time interval over a span where I can consider G to be approximately constant. This completes variable mass.